Hello, and welcome to the second part of Lecture 22. We're going to continue to discuss rolling motion. So we're going to start out our examples with an example of a purely rolling ball down an incline. All right, so let's take a look at it. So we have a sphere, it's rolling down an incline. We're given some values for all the relevant dimensions and masses and so on. Okay, so how do we set this up? Well, so we have a sphere. We're told its mass, radius. Okay, we're told the angled incline is 18 degrees. That's our theta value there. And we have a height of 0.85 meters, right, 85 centimeters. So using forces and torques, what is the acceleration of the sphere as it rolls down the incline? In fact, there's no way to solve that other than using forces and torques. That is, I just write that there as a reminder. Okay, there's no way to do this with energy, for example, because energy tells you nothing about acceleration. So, a couple things here. We want to set up a sum of torques, sum of forces. Okay, we've done this before for other free body diagrams that involve torque in the last lecture. It's just here we're doing it for a rolling object. Okay, so just very similar to what we would do for a pulley. Okay, or a real Atwood's machine where the pulley has mass. Okay. All right, so but that means we got to choose a pivot. Okay, so I'm going to be kind of consistent here, or maybe a little rigid in my thinking, and I'm basically going to stick with always choosing the center of mass as a pivot. You can really choose a pivot anywhere you want. We're going to have more practice with this when we do what are called equilibrium problems, which are more complex kind of systems of beams and wires and so on, where we can make lots of choices about where the pivot is located. And in doing so, it can simplify our work or make our work considerably more difficult. In this case, there's really not a huge advantage to choosing the pivot elsewhere. Because if you think about it, if I chose the pivot to be, say, the contact point between the ground and the sphere, so right there, if I'd chosen that as a pivot, it would be equally advantageous, okay? And what do I mean by that? You know, what's advantageous or disadvantageous about it? Well, it's all about how many forces create zero torques. So if I look here, if I look at my chosen pivot, I have a normal force that creates zero torque because there's going to be no component of that normal force that is actually going to be contributing to the pivot, right? So in other words, it's parallel to my moment arm, okay? So the normal force is parallel to the moment arm. Now, how do I know that? Well, think about where the normal force actually acts, because forces, now their location matters, right? If that hasn't become obvious, it really should, okay? The location matters, it matters, it matters. And so then the normal force is applied at this point right here. So even though the picture kind of does a bad job of showing the normal force, right? It shows it maybe like that it's a dotted, that it acts at the center of mass. It actually acts at that contact point. But most importantly, the moment arm, which is this distance right here, make that a little bit thinner. Let's go with that. Okay, so this is our R, okay? So when I take a look at that R value, that moment arm vector, I have that the normal force vector is anti-parallel to the moment arm vector, so they have an angle of 180 degrees. Well, when I take sine of 180 degrees, I get 0. Okay, so there's no torque that's created by that normal force, even though the force is not acting at the location of our chosen pivot. On the other hand, our gravitational force just acts at the pivot in the story, right? So right there, it's being applied at the location of the pivot. So in its case, it has a moment arm of length 0. So that also means 0 torque. Well, that means the only force that's actually creating torque is the friction force. That has a moment arm that's the same length as the moment arm as the normal vector, but that force, the friction force, points perpendicular. So we're going to have a sine of 90 degrees. Okay, so it's going to be non-zero. It's actually just going to be force times moment arm, because sine of 90 degrees is, of course, 1. Now, if I'd chosen the pivot to be down here instead, well, in that case, I would have the friction force create 0 torque. The normal force would still create 0 torque for the same reason as I mentioned before. But now the gravitational force would create a non-zero torque. Okay? All right, so let's get to it. So with our chosen pivot point, we want to set up our sum of torques. So I'll go ahead and do that first since we're already talking about torques. So I have tau net, then is just going to equal the friction force times the radius, which I call R naught. I'll go ahead and label that in the picture as well, because our moment arm is exactly equal in magnitude to the radius. Okay, and then that's going to equal the moment of inertia of the sphere times alpha. Okay, then that's going to be the sphere, the moment of inertia of a sphere about its own center of mass, because that's the chosen point for the pivot. If we'd chosen the pivot to be the contact point, then we'd actually have to use the parallel axis theorem on our moment of inertia to take into account that shifted pivot point. So we would mean the moment of inertia of a sphere rotating about its edge, which would be 2/5 mr squared plus mr squared, right? Okay. Consult the parallel axis theorem to confirm why that is. Okay. But in this case, we don't have to do that. We can just take the published value of 2/5 mr squared, and we're done. Okay. And then that's also the one that we showed using a calculus trick, right? And then we go down to our f net x. And what's going on in the x direction? Okay, so we're using these axes, tilted coordinate system, positive being downhill. All right, positive x that is, positive y, just normal to the surface. Well, in the x direction, we've got a positive component of gravity. That's this one here. So we'd have mg sine theta. And then we'd have to subtract the friction force. So subtract f sub f. And then that equals simply ma. Okay? Because again, this rolling object is both accelerating in rotation and accelerating in translation. Then we also have F net y, which will help us solve for the friction force. F net y is simply going to be Fn minus mg cosine theta, and that one's going to be equal to 0 because there is no acceleration in the y translational direction. Okay, so then let's use our equations to simplify friction. So we'll say thus. All right. Switch to a smaller pen, right? So I guess we'll leave our key equations in the large pen, then we'll move on. So thus, Fn equals mg cosine theta. All right, let's go ahead and turn that airplane mode. Okay, so mg cosine theta, that's again just from our sum of forces in y. And so that means that our friction force is simply going to be mu k, or actually mu s, mg cosine theta. Why mu s? Because we showed with our relative velocity, with our very baseline assumption about pure rolling motion, which this problem is pure rolling motion, the point of contact right here, right, that point of contact is not actually moving relative to the ground. It's fixed relative to the ground. When it moves, it lifts up, right? So it's like the point comes into contact, lifted back up, lifted back up, lifted back up, right? Touches, lifts, touches, lifts, and so on. Okay, so that means there actually is no kinetic friction. It's static friction because it's at rest relative to the ground in an x motion sense. All right. So then we'll go ahead and substitute in that friction into our net torque. So we'll line this up over here. So substitute friction equals mu s mg cosine theta into tau net. And then that's going to give us mu s mg cosine theta r naught equals 2/5 m r naught squared times alpha. Okay? Okay, now we do another substitution. Okay? Or I should say another definition, right? Because this is pure rolling, we know that alpha equals a times r. A over r, excuse me. So alpha, which is the angular acceleration of the object as a whole, right, that doesn't represent any particular point, would be equal to the acceleration of the center of mass divided by the radius of our sphere. We call r naught in this particular problem, okay? And just to kind of call attention to that, I should have right here, because I'm trying to make that clear, that acceleration, this translational acceleration, is none other than the translational acceleration of the center of mass, okay? Now, could we be interested in other accelerations? Sure. We could talk about other translational accelerations relative to the ground, because that's what that's what that acceleration represents, of other points on the sphere, okay? But that would be more of a follow-up step, right? When we solve the problem, we need this relationship, and this relationship represents or relates the center of mass to the overall rotational motion. Okay, so make sure you know what the equation means, right? Because if you blindly write alpha equals a over r, you might confuse yourself and think, well, what a is it? Well, it's the center of mass acceleration. Okay, so from here, we can just make a couple more substitutions and get a nice result. You'll see that these problems clean up incredibly well by their very nature. So I'm going to rewrite our torque net, all right? So if we rewrite our torque net equation, I have mu s m, oh, this should be a big M. Yeah, I see. I wrote it as a little m too many times. So it's a big M, okay? and that's a big M, and that's a big M. And this one over here is a big M. Okay, sorry about that. So there is no little m in this problem, but I don't want to be switching my variable. It's my own fault for having a mixture of lowercase r and uppercase m. It confuses me. Okay, there we go. All right, so big M, G, G, and then we'll go ahead and put our r naught over here, cosine theta. All right, and then that's going to equal 2/5 m r naught squared times a over r naught. Okay, and let's think about some cancellations here. So we should have a very nice set of cancellations. Okay, so I have an r naught cancel of one of those. I also have an r naught on both sides, so then those cancel. I have an m on both sides, which cancel. So that means when I actually solve for my translational acceleration, primarily from using the torque equation, but again, it's up to you how you approach the algebra, I end up with a result that tells me that my basically mu s mg cosine theta just equals 2/5 ma. So let's see, what's the best way I want to do this? I guess I just want to go ahead and solve for a. Let's see, if I went ahead and solved for a in terms of mu s and everything, then I could substitute it in, except I'm trying to solve for the acceleration. So what I'll do instead is I'm just going to go ahead and kind of oversimplify or overcomplicated step here, but we'll kind of carry on. It's not a big deal. I really probably shouldn't have split up the friction force like I did into mu s mg cosine theta, since I'm interested in ultimately back substituting this back into the net force, and I really want to express the friction force. So I'm going to say just kind of and mu s and then mg cosine theta, well, that just equals the friction force. And then we can see that that's just going to be equal to 2/5 times ma. Okay, because that's just the result that we have here. And that would be getting rid of the canceling out m's. So let's not cancel them out. Okay, there's just no need to at this stage. So 2/5 ma. And the reason I'd want to do that is because now I can, as I said before, and substitute this back into net force in the x direction. So F net x. And what does that give me? Well, that's then just going to give me mg sine theta minus 2/5 ma equals ma. Okay, and so then if I go now is a good time to cancel the m's, because now I have a good opportunity to do so. And then I want to go ahead and solve for the acceleration, which is what I sought to do. So if I added 2/5 to both sides, I'm then going to have a 7/5. So I'll have g sine theta equals 7/5 a, or simply a equals 5/7 g sine theta. Okay, so in this case, that's 2.16 meters per second squared. Okay, for this particular value of gravity on Earth, 9.8, and for our particular angle, which was 18 degrees. Notice what doesn't matter. The mass and the radius have no effect on this final answer. None. Okay, so this would be true of any sphere. It doesn't matter how large the sphere is. It will always accelerate at the same rate. It doesn't matter how large in radius or mass the sphere is. Okay, its translational acceleration will always be the same. Its angular acceleration will be independent of its mass, but will be dependent on its radius. Okay, but its translational acceleration of its center of mass is independent of both its mass and radius. Quite interestingly. Okay. What does matter, of course, is the shape. That's where the 5/7 come from. That's unique to a sphere. And the planet and the angle matter as well. Okay? That's the g and the theta. Okay, so in part B, if the sphere is released from rest, what is the velocity of the ball at the bottom of the incline? Okay? So there's two ways we could do this. We could use just conservation of energy because we have, the release height. So we could easily use conservation of energy to find the final height. Or we could use kinematics since we already have the acceleration, and then we could then just use the the distance, because we're told that the it has, we could find its length, right? We could find L based on h and theta. Okay, so let's go ahead and do that since we already have the acceleration. So we'll say since we already know a com, okay, and that's in x direction. It's the only translational acceleration. There is no translational acceleration in the y direction. We can use kinematics, and we'll simply have that v squared equals 2a com x times L, where we have sine of theta equals opposite over hypotenuse, so h over L, which then tells us that L is just going to be h over sine theta. Okay, and so then if we do that, we then have that v is going to be the square root of (2a). Okay, so it's going to be 2. A is 5/7 g sine theta. Okay, and then we'll multiply that by h over sine theta, like so. All right, and of course then the thetas cancel out, or the sine thetas cancel out. And so then, which it should, because gravity is path independent and there's no friction here, so we should then just be able to find the, there's no friction doing work, that is, right, pure rolling. There is friction, but it's not doing work. That's the thing, I know, it's hard to wrap your head around. But then, so we look here, then that result would simply give us root 10/7 GH. Which is exactly the result you would get from conservation of energy by just setting up a, mgh equals, and then just take both forms of kinetic energy at the bottom, the rotational form and the kinetic form. Okay, and so then that just gives us, I'll actually go ahead and show that to you really, really briefly. And that just gives us 3.45 meters per second. Okay, and then just that promised quick note of how you can do with energy, because you haven't seen that too much, so I want to at least show you that approach. And I'll say, and we could use energy instead, and of course energy is shorthand for energy conservation, mechanical energy conservation. And what that would look like, that would just be mgh, and then that would become all kinetic, because when you get to the bottom of h, all the gravitational potential is gone. So it would just be 1/2 I omega squared plus 1/2 mv squared. And then just quickly, this would become 1/2 times 1/2 m r naught squared. Omega would be v over r naught. Okay, and then when you went ahead and solved for that, because you think about what's happening, oh, it's not a 1/2, it's a 2/5, because it's a sphere, not a cylinder, excuse me. Right, so when we actually, if you think about these two terms here, this one here would become a 1/5. 1/5 plus 1/2 is going to give us our 7/10, I believe, and then it should. And then when we go ahead and then solve for v, then we're going to take the reciprocal of that, which will be our 10/7, and that's our final result. Yeah. So yeah, 1/2. Yeah. Yep. 1/2 plus 1/5 is indeed 7/10. Okay. So you can see get the exact same result. So that helps make a little arrow here. That just brings us back up there. Okay. So absolutely, you got choices there on your approach. We're asked then to find what is the minimum friction. What must be the minimum friction force provided by the surface of the incline? I'm actually going to go ahead and solve for the friction coefficient as well. I think it's a bit more clear, but I'll answer the question that was given to us first. All right. So, okay. Let's think about that. Minimum friction force. Okay, so when I'm asking for the friction force, so I even say minimum, I guess. I was thinking minimum, but that's what I mean, right? And if there's any more friction than that, it doesn't matter because that friction isn't doing work. And the friction could never stop the ball from rolling, right? The friction is simply going to stop it from slipping. It's going to roll because of gravity. You think about there's gravity in a certain direction, it's going to tip. There's nothing to stop it from tipping. There's no way that friction force could ever stop it from tipping, okay? And so when we solve for that minimum friction force, that's exactly it. It's the minimum, okay? So the friction force represents the minimum friction force to prevent slipping. Because we assumed pure rolling. We assumed pure rolling because we were able to use this relationship right there, okay? So the friction represents the minimum friction force to prevent rolling, or sorry, prevent slipping, not prevent rolling at all. And so what does that look like? Well, it's simply, okay, well, if I go back, then I can just plug it back in, right, rather easily. I already know that friction force is 2/5 ma, so notice the mass matters here. And so now we're finally using that value because we're finding a value of friction. So we'll put in our 1.5 kilograms. We'll put in the a that we solved for, 2.16 meters per second squared. And we get 1.30 newtons, okay? And then the friction coefficient that I want to give you as well. And mu k then would just equal that 1.3 newtons divided by Fn, which is just going to be mg, let's see, it was mg cosine theta. All right, so 1.30 newtons. All right, and actually here, let's write it symbolically here, this step. So then it would be 2/5 ma divided by divided by mg cosine theta. And so then we're going to get 2/5 a over g cosine theta. So just our 2.16. And actually, what's our form of a? So our a has the form of 5/7 g theta. So let's write it like that. So it'll be more clear. So 2/5, the m's canceled here. And then our a is 5/7 g sine theta. Our Fn is, well, what's left of it is is g cosine theta because the m canceled. So that's g cosine theta. So we can see the gravity cancels, which it should, okay, because this result, the friction coefficient should work regardless of gravitational acceleration. There has to be some downward acceleration. And so then we end up with a tangent, and we look at it, and so I got 2/5 times 5/7. Nice. So the 5's cancel, so this is 2/7. Okay, so it's 2/7 tangent theta. All right, and so it's such an interesting result because this is still an accelerating object, right? So it's not like, say, finding the friction coefficient that we did when we had objects that were sliding, and we're finding that the friction coefficient was just equal to g times just equal to tangent theta for the friction coefficient that was necessary for an object to slide down a slope at a constant velocity. Here we're having something that's absolutely accelerating, so it's still speeding up, but we're having it so it doesn't slip. And that condition ends up with a also very simplified result, which is 2/7 tangent theta. The tangent theta is going to be there for any shape, right? This one will always be there. The 2/7 is just unique to the fact that it's a sphere. So then when we plug that in, let's just see what I get. So 2/7 times tangent of 18 degrees, and that gives me, oh, I have a typo. Okay, that gives me, oh, it's all right. Tangent 18. Okay, make sure I'm in the right mode. Yep, degree mode. Okay. So yeah, so 0.093. So 0.093. So if there's less friction than that, then our object would slip. Because in that case, it wouldn't be enough friction for it to kind of pivot around that point, because you can think of that point as a pivot as well, and we could have even used it mathematically as a pivot. There'd be too little friction here, and so it would actually slide. It would still start rolling. Okay, it would still start rolling, and it would start to speed up until it reached a case of pure rolling. And at that case, we'd be fine. We then would maintain pure rolling. But at first, there would be some slipping. There'd be translation that wasn't directly related to the rotation. Well, I've talked so much about slipping. Let's look at and the next problem is an example that does include friction, includes slipping. And the idea here is that for the next couple of examples, I just want to show them to you in kind of somewhat quick succession, is that they are just going to be narrated. I'm just going to kind of go through, and I already have the work written out. I'm just going to kind of show you what I did in the interest of time. Okay, so in example 2, we have a bowling ball of mass 5 kilograms and radius 0.12 meters. It is thrown parallel to a level surface so that initially it slides with a linear speed of 3.04 meters per second and does not rotate. So this is an object that starts with pure translation and no rotation. However, as it slides, the force of friction begins to spin the ball until eventually it rolls without slipping. Okay? And so that's the idea. It's transitioning from rolling with slipping to pure rolling. Okay? And the friction coefficient is 0.211. Okay? So I made sure that the friction coefficient would be enough for pure rolling. In fact, actually, in this case, because it's level ground, any friction coefficient would be enough. Even if I had a tiny friction coefficient, that just means it would take longer for it to stop slipping. And the bowling idea is meant to be accessible, because if you actually think about the times you've thrown a bowling ball, if you have, or if you kind of just visualize that from seeing it, that when you throw that bowling ball, it actually is at first slipping primarily, and then it starts to roll. And that's because it's a rather smooth surface, and so we actually are able to see that phenomenon of slipping, transitioning to rolling. Sometimes it continues to slip, right? If you throw it particularly fast, so your V0 is very large, you might have a ball that continues to slip all the way down until the pins. But it's better for it to be rolling, right? That's why they say not to throw a bowling ball too fast, because if it hits the pins while still purely translating or mostly translating without much rotation, it's not going to really deliver its angular momentum, because it doesn't have any, more on that later, to the pins, and thus not really allow the pins to really fly and hit each other. All right, so 2 steps to this problem. We're going to write the sum of torques about the pivot. Right here I have the sum notation rather than the word net, and the sum of forces. And we're going to do that in order to find angular acceleration and translational acceleration. And that, of course, is translational acceleration of the center of mass, which for simplicity, I just write as A. We're then going to use kinematics and the condition of pure rolling, which is none other than V equals omega r, right? That's going to be once pure rolling starts, slipping ends, once friction stops doing work. And we're going to do that to find the time for pure rolling. Because in part A, the question is how much time passes. And then part B, how far will it travel before it starts pure rolling and stops slipping. Well, once you have the time, we can easily find the distance, just continue to use kinematics. Okay, so what does this look like? What's because this is such an interesting process here. Okay, so the beginning, the setup, the sum of forces is really quite similar to what we did in the previous example. Okay, so we have a sum of torques. Okay, I have a single torque created by the friction. Why is that? Because I've chosen the same darn pivot, the center, right? It's a nice natural choice. So then the friction is the only force creating a non-zero torque relative to that chosen pivot point. That's going to be equal to I alpha. In this case, I is going to be the moment of inertia of a sphere, again, just 2/5 mr squared, okay? So then I go ahead and solve for alpha, right? I'm just going to symbolically start down and do that step. And when I do that, I get that alpha is equal to the friction force times r naught times sine of 90, which is just 1, and then divided by I, which is 2/5 mr squared. This simplifies a bit because we're able to cancel out one of the r naughts, and then we can then rewrite the friction force as simply mu k mg. How do I know that? Well, I'm going to get that right from here. Okay. So from the sum of forces in the y direction, because it's not even slope, is very easy. It tells us that the normal force is just equal to mg, in other words, the weight. And then by definition, the friction force is mu k times Fn. So in other words, the friction force is just mu k mg. So I can then substitute that in up here, which allows me to cancel out my m's. And so then you can see that I have that the angular acceleration is mu k divided by 2/5 r naught, which are the right units of, mu k times g over divided by 2/5 r naught. And those are the right units for angular acceleration because it should be a translational acceleration like g divided by a radius, right? So it's got radians per second squared. Okay, so that's great. Then I do the same sort of thing for acceleration. In this case, I'm going to use my sum of forces in the x direction, which is just friction, and it's just going to equal ma. Here I don't identify a as negative or positive. The equation will tell me whether it's negative or positive. And indeed, it tells me that acceleration must be negative because there's only one friction, there's only one force, and it points backwards. So my acceleration must also point backwards in the negative x direction, right? Back this way. And so then my translational acceleration is negative mu k g. Now here's where things differ from the previous example. Before, I would have used the relationship that alpha equals a over r, or that a equals alpha times r, because that's true as long as you have, a pure rolling system, right? But the translation and the rotation aren't synchronized here. It's not purely rolling. So they're definitely not equal to each other. So I'm going to be like, well, if they're not equal to each other, then how do we even proceed? Well, we got to find out how long it takes until they become equal to each other, all right? So that takes us to step 2. So in step 2, we jump right into kinematics, okay? So these are going to be the kinematics of the object as it transitions from slipping to pure rolling, okay? So I write out my velocity equation for translation and my velocity equation for rotation, okay? And this is really what you would do for any problem involving slipping. Now here, my velocity equation for translation has a non-zero v naught because my system started with all translation, no rotation. And then it's got a times t. And we, of course, know the form of at from our sum of forces. Likewise, if I look at my rotational velocity equation, I have a similar result, except omega naught is 0 because the system started without rotation. Now here's the thing. I'm going to take these two equations, okay, and set them into our pure rolling condition, because then I'll have an equation that will have a t in it, which will tell me how long it takes until this condition is met. Because once v equals omega r naught, then slipping's over, right? So I just plug in my v as v naught times v naught minus mu k gt. Where did that come from? Well, remember that a was just negative mu k g, so there we go. It makes sense here that this term is v naught minus something, because it's essentially saying that the maximum translational velocity is the initial translational velocity, because friction starts to do work. Friction starts to do work to remove kinetic energy and create rotational energy, okay? It's also, is it a direct relationship between the two? Is it creating as much rotational energy as the translational energy is taking away? No, it absolutely is not. Okay? It is removing mechanical energy from the system, but it's not just removing translational mechanical energy and only producing heat. It's also giving us something else. It's giving us rotational kinetic energy. And we can find out exactly how much rotational kinetic energy it gives us by finding out, how long it takes to fill until pure rolling begins. And so then the other side of the equation, the omega naught r side, is simply plug in the fact that omega is equal to alpha t. We know the form of alpha from our sum of forces and sum of torques, and we know it's just 5/2 mu k g t over r naught. And then since we're multiplying that by r naught, well, the r naughts cancel. Well, of course they should, because we need to have like terms on both sides of this equation. And so then it's simply a matter of solving for t, right? So we go ahead and have this here, right? So this becomes the equation, because all I've done here is just add this term to both sides. And so then I have two terms equal to v naught. So then I eventually just solve for v naught, but then I solve for t. Okay, so then I back up and solve for t, and I end up with the value that was given for v naught, which in this case was 3.04 meters per second. My t, when I plug that all in, my t ends up being about half a second, 0.553 seconds. So not very long, right? because the friction was not tiny here. Okay. Furthermore, I then can find out that the final velocity is 5/7 of v naught, right? Because if you think about it, once I have, if I plug this result back in for t, right, because of this symbolic result for t, if I plug that back into my velocity equation, then I have this really fascinating result. It tells me that for any sphere that begins with purely translation and no rotation, by the time it stops slipping, it'll be traveling 5/7 its original translational velocity every single time, okay, for any sphere. It's independent of the radius, it's independent of the friction coefficient, it's independent of gravitational acceleration, it's independent of the mass. It's only dependent on the fact that it has the shape that is a sphere. So it's so fascinating, okay? All right, so one other thing is part B. I actually didn't solve for part B yet, so let's make a little bit of space and I'll go ahead and solve for that now. Just shrink this down a little bit because I just want to, it's a quick result. So let's resize this a tad, bring it up, okay. So how do we actually go about doing that? And I want to show you because I don't have another step where I show it to you, so it's important. So in part B, how far does it go? How far does it go before it stops slipping? So distance traveled until slipping stops and pure rolling begins. All right, well that's then simply going to be we'll just use translational kinematics to find that. So we'll use x equals x naught plus v naught t plus 1/2 a t squared. Okay, so that's going to be L, I'll just call that the distance. Okay, and x naught will be 0. Our v naught we know is going to be, it's given. We know our t has the form of 2/7 v naught over mu kg. So then this is just going to be 2/7 v naught over mu kg. All right. And then over here we have our A. Our A we know to be negative mu kg. So negative mu kg. And I'll plug in the same result for t. So 2/7 v naught mu kg. This time we're squaring it. Okay. So those are going to give us like terms. Okay. These two here. These are both like terms, as they have to be, right, in terms of dimensions, but we can directly combine them. So let's just think about it, right? What will they become? So they're both going to have the form of v naught squared over mu kg. You can see that kind of just by looking at it, because we have here an excess mu kg because it's squared, but one of them will cancel, all right? And so then, and there's a negative here, right, because the negative would come out. So then essentially this is going to be 2/7 minus, so it'll be 2, I'll just write this in parentheses so you can see my reasoning here. So it'd be 2/7 minus 1/2 times 2/7 squared. And that's all then going to be multiplied by v naught squared over mu kg. Okay? And so then if I plug in and just get a fraction result for this, I like to leave these as fractions because they work out so nicely. So 2/7 minus 1/2 times 2/7 squared. So that whole bit becomes 12/49. All right. And then just v naught squared over mu kg. Okay. So we can see that it's a greater distance if it's a greater initial velocity. It's a greater distance if mu k is really small or if gravity is small. And so then our final result will just be, let's see, so did not leave myself enough space. I don't want to continue to crowd that in since everything else is so widely distributed. I don't want part B to be quite so crowded. So let's try to give ourselves a little bit more space. There, that's much more legible. Okay, and actually we'll make it a tad larger. Okay, so let's plug in that final number. So 12/49 times 3.04 squared, and then divided by 0.211 times 9.8. Okay. All right, everything's good. So 1.09 meters. Nice distance. There we go. All right, that's how far it goes before it starts to purely roll. And then we'll continue to go, right? Because in this case, lean level ground and all, once this bowling ball starts to purely roll, it would just purely roll forever. Okay? Now, of course, that's because it's ignoring drag or the fact that there's not a single contact point in the real world, okay? All right, so just quick rundown on a couple more. So in this problem, I have a hoop and a solid cylinder. I give you their masses and radii. They just have a 1 and 1. 1 meter and 1 kilogram, that is. And then the slope here is 31 degrees, so it's quite steep. I give you the height again, so very similar to example 1 in that regard. And the question is, what initial velocity would the hoop need in order to reach the bottom at the same time as the cylinder? Okay? Well, that means that we need to find their accelerations and then to make sure that they cover the same distance in the same amount of time. Okay? And the reason that I know it's going to be the hoop that's going to need an initial velocity is because the hoop, having a bigger moment of inertia, will have a smaller angular acceleration, which means it'll have a smaller translational acceleration, which means it's going to lag behind the less inertia, the easier moved cylinder, okay? Because the hoop is harder to move, it's harder to rotate than the cylinder because all of its mass is far away. It's got, it requires more torque and all that. And so the idea then is that the only way for them to arrive at the same time is to give the hoop essentially a head start, or to give it a push, so it starts off a little bit faster. So the approach here is I go ahead and find the angular acceleration. Notice this, though. This is a very interesting result here. I kind of set this up as a general for any shape, so I don't plug in the particular form of the moment of inertia for either the cylinder or the hoop. I just leave it as a variable I throughout all of the calculations. So you can kind of you can see I just leave I as I go ahead. And again, I start with the same approach. It's pretty small over here. But just like with the previous two problems, I start with the sum of forces in X, the sum of forces in Y, and the sum of torques. Okay, we've seen that. Pay attention to any differences. There really aren't many. I chose the same pivot as the center of mass, which I've done for the previous two examples. But what is interesting is since I left it in that form of not substituting in a particular moment of inertia, but since leaving it as I get this quite general result. This tells me that the translational acceleration of the center of mass of a rolling object down an incline will always be equal to this, g sine theta all over 1 plus moment of inertia divided by mr squared, right? So then you can just plug in whatever moment of inertia you want. In this case, we'd plug in mr squared for the hoop and 1/2 mr squared for the cylinder. So then for the kinematics, since I want them to arrive at the same time, I want the time of transit for the hoop to be equal to the time of transit for the cylinder. And then, so I set up the following equation, x equals, right? And so that's my x, because that's just the length of the ramp, just like in example 1. And then, so this equation right here would be for the hoop, which is why I have the moment of inertia of the hoop. The next one over, I wrote it all in one line, this would be the moment of inertia of the cylinder, right? So this one right here is I cylinder, right, which is 1/2 mr squared. Okay, and then what I can do is I could then use either of these equations, right, because these are both independent equations. This equal to this is one equation for motion, and this motion here equal to that is the other equation of motion. They share the same t, and that's important. But I can use the first one, translational motion, translational displacement equation. For the cylinder as my first case. What happened? Okay, so I could use that to find the time. Okay, so that's all I do here is I find the time using the motion of the cylinder. I know that must be the same time, so then I just back substitute that time expressed in terms of the height and gravity and the angle. I then substitute that back into the motion for the hoop, and then I can go ahead and solve for the initial velocity. Because notice, right, of the two motion equations, both at the form x naught plus v naught t plus 1/2 at squared, only the hoop had a non-zero second term because it's the only one with a non-zero initial velocity. The cylinder, of course, had an initial velocity of 0 because it didn't need a head start, right? It didn't need a push in order to tie in the time it takes, okay? And so then I get the final result that hoop needs a little push, and in this case, based on the length of the ramp, right? Or really based on the height, because notice it is what, if we notice what it's dependent on, our final result is dependent on the height, on the planet we're on, and the shapes, which that's why we have the 1/4 and the 1/3. Okay, and so in this particular case, you got to give it a 70 centimeter per second push in order for them to tie. Okay, and if it was a much larger ramp, a much longer ramp, the push would get bigger and bigger, right? Because it would have to, you'd have to really compensate for the cylinder having more and more time to get out ahead. Okay. So hopefully that's interesting. I left a practice problem for you to solve on your own where it looks quite similar. You might think it's the same problem, except instead of them having the same, for the reach at the same time, I want them to have the same velocity at the bottom. So one initial velocity with a hoop needed in order to reach the bottom at the same time as the cylinder. Oh, that's a typo. Sorry about that. In this case, it's supposed to say to reach the bottom with the same speed as the cylinder. So let's cross that out and fix it. So this time I don't really care which one gets there first. I just want to make sure they get there with the same speed. So this one you could actually use it entirely with energy, right? Okay, you could do it with forces and torques and accelerations and all of that, but you could also just use energy, which would be a whole lot easier. So it's kind of interesting when you can and can't use energy. Remember, you can never use energy for any equation that directly asks for a force and acceleration or a time. You can use conservation of energy approaches for any equation that asks for a velocity. Okay? So initial velocity with a hoop needed in order to reach the bottom at the same speed. Oops. At the same speed, okay, as the cylinder. All right, then we got another one for practice. This is another rolling with slipping problem. Definitely a good one to practice if you feel like that those steps are mini and complicated. This one I'd like to show it to you, but in the interest of time, I won't include it in today's lecture. And then we finally have one other example. This one is from a past exam. Just a fascinating combination of slipping on a slope, which we haven't seen, right? We saw the bowling ball slipping on level ground. What about an object that's transitioning from slipping to pure roll